All right, let's go ahead and take attendance. All right, let's begin. Okay, so I'm going to start up Jupyter Notebook. Go to my 131 folder, and this is 2019 Fall Stats 131. Okay, we'll see how quickly, how far we can get through the content. Maybe we won't cover everything. And again, what you're going to want to do is you're going to want to, run your Git program. So you'll want to navigate to your folder, and you're going to want to do a git fetch upstream, okay, and then merge upstream master. You might even be able to do git pull. You can also do git pull upstream master directly, and I think that will go ahead and that will fetch and merge the changes that I've made to my repository into yours. Okay, so if you have your remote repository set up on Git, then this should work. Okay, and then and so today I'm going to work through this file 0201, and in order to avoid merge conflicts, I recommend that you make a copy of this file. So as soon as you complete the pull, go ahead and make a copy of it. Rename it to with your name in it or something, and that way, because what I'm going to do is, as I work through this, I'm going to be making changes and edits to it, and you likely will also be following along, making some changes and edits to your notebook, and if we both make changes to the same file, we're going to have a merge conflict, and merge conflicts with Jupyter Notebooks are not easy to resolve. It's possible, but it's not easy to resolve. So I encourage you to make a copy. You work on the copy, I'll work on the original, and then I'll push all of my changes, and then you can commit your changes and merge my changes into yours. And you will just end up with 2 copies of basically each lecture notebook. 1 copy with your notes and 1 copy with my notes as well, okay? Or if you don't want to do that, you can just not commit any of your changes and just wait for my changes to be pushed and published. But if you want to make changes and save them and commit them, I strongly encourage you to do it to a copy rather than the original to avoid merge conflicts. Does that make sense? Okay, I'm going to go ahead and I'm going to open up this notebook, 0201, and we covered the beginning stuff. Okay, so so as I run through, it says this comment is not run, and then I'm just going to hit Shift Enter And we already talked about these ones where you can, semicolons will allow you to put multiple kind of commands on the same line, and you can extend your entries over multiple lines with the backslash or any kind of bracketing parentheses character. Okay. We also talked about on Friday how code blocks are defined by indentation. Okay. There's no curly braces, and that's what we have here. Okay. So the difference between these two is only the indentation, but it significantly changes the way the code is executed, because only the indented lines are associated with the if statement. Okay, are we so far so good? So where we left off? Okay. All right, and so now we'll start talking about our data types that exist in Python, and these are I think we're familiar with these. Okay. So we have two numeric types. I mean, technically you also have complex numbers, but the ones that you're probably going to be interacting with most will be the integers and the floats. Okay, so you have int and float, and these are in R we call them integer and double, and in Python we call them int and float. All right. If you type in the number 3, it's going to be an int. All right, and you can ask what type a particular value is by using the function type. So you type in type. In here I've got a 3, and that's an int. If there's a decimal point, it's going to be a float. Okay, so 3 with a dot is going to get classified as a float. Okay. Okay. Here I'm storing, saving the number 10 into object A. So what will type A be? Type A is an int, okay? So A is 10, 10 is an int. And B is 2, type of B will also be an int, okay? So when you just type in a number, in Python, it defaults to int. Okay, if there's no decimal or anything, it's just gonna default to an int if it just sees a whole number there. All right, that's different behavior, different from R. Right, the default behavior in R is that when you type in the number, it's going to be typed double. But here, it's an int. Okay. Python will automatically what it calls upcast. It's the same thing as coercing in R, but the vocabulary is that it's called upcasting. So in our case, we see that A and B are both integer types. Okay, and whenever you do division, it's always going to result in a floating point number, even if the answer is a whole number. Okay, so 10 divided by 2 is 5, but Python, whenever you do division, the result will always result. The value that's returned is always going to be a floating type. Okay, so here I'm going to do C is A divided by B. So inside C, we're going to see 5. Okay, the print is going to appear on the screen. Okay, so we can see how 5 is stored, and then it will tell us the type. Okay. So when it does 10 divided by 2, it returns 5.0, okay? And we print that out, and the output of type C is a float. Okay. You can do integer division, okay? And this returns the whole number part, and it will be type integer, okay? So 11//3 will be 3, okay? So it's 3 remainder 2, and here it gives me back 3, okay? So //3 gives me the remainder, not the remainder, the whole number part of the dividend. Is that what the word is? I forget. You have the quotient, yeah. The dividend, the divisor, and the quotient. I don't know. Are those the parts? Okay, the quotient, the whole number part of the quotient, okay? And we can tell, even though I didn't do a type of this output, we can tell it's an integer because Python does not display decimal. When it's a float, it will display 5.0, okay? If this were a float, it would display 3.0, but it doesn't, okay? And of course, I can do 11 divided by 3, and then it shows up as the integer, not integer, as the float. Okay. All right. It's good. Okay. Floats are always represented with a decimal point, even with a whole number. Okay. And so A is once again A is 10 and B is 2. Okay. So A is 10 and B is 2, and they are both integers. And when I do A times B, it's going to return 20, okay? 10 times 2 is 20, and it keeps it as an integer, right? So integer times integer will return an integer, okay? But anytime you do division, it's always going to be a float, even if it's integer or not. So 10 divided by 2 is always going to be float, okay? Here I have 5 point, so just the fact that I put the point here makes it a float. Okay, so I got float times an integer. I don't know why this. Float times an integer, and so this will return, what will it print out? So 5.2 times 2 will print out E, which is 10.0, right? It's going to print out 10.0, and the type will be a float. Okay, because this thing goes right there. Okay, so here's an interesting thing about Python's behavior, is that integers are variable precision, okay? So you can do really big calculations without running into overflow errors, okay? So in R, the biggest thing you can do is 2 to the 31, or actually 2 to the 31 would cause it to overflow. But you can do 2 to the 30 for type int, and that will work. But if you try to do a integer type for anything bigger than this, R fails because it allocates only a certain amount of memory, and more than that, any number bigger than this requires basically more digits or binary bits in the in memory, and so it fails. But I can do 2 to the 1023 power in integer, and it reports back this really big number. Okay, 2 to the 10 to the 24 power reports even bigger number. It's twice the size. Okay. This is not the case with a float. Okay. With a float, if I do 2.0 raised to the 1023, it gives me a number, right? We get something just about the same, 8.9884656743115, and it rounds up to 8 here, okay? Times 10 to the 307, all right? So on a double precision floating point, how many bits do we use to store the number? We use 64 bits, right? We have 1 for the sign, 11 for the integer, and 51, okay, I don't know, 52 for the mantissa. Okay, but anyway, you're limited, right? And so once you go over, I think the 11 bits, meaning the kind of the biggest integer you can use is exponent that you can use is 1023. Once you go over that to 1024, you get an overflow error, right? You get overflow error. Whereas with the integers, because it's variable precision, Python says, okay, just keep using more memory. It's fine, okay? keep using more memory, we can store it, and it works. So 2 power sign, the power sign is 2 multiplication, or 2 asterisks. 2 raised to the 1024 power is this, okay? This is something that just takes a little getting used to, using 2 asterisks for power, especially when you've been used to using Shift 6, the caret in R. All right. So that's kind of neat, okay? And then, and again, regarding floating point numbers, because floating point numbers are implemented at the hardware level, the same kind of floating point number warnings, you have to heed them, right? So Q is 0.1, R is 0.2. If I do Q plus R, we would get 0.3. We actually get a little bit of a sense that it's not exactly equal. So when I do 0.1 plus 0.2 and I say print S, we do see that it's not equal to 0.3. And if I ask is S equal to 0.3, I get back false, right? So 0.1 is technically not 0.1 and 0.2 is technically not 0.2 because we're approximating them using our binary system. All right, is that good? Okay. Your true and false values are called bools. In R we call them logical, but here we call them bools for Boolean values. And you write them as true, capital T, lowercase R-U-E, all right? Any other spelling, if you do all caps true or all caps false, like you might be accustomed to in R, it's not gonna work, okay? So it's capital T, lowercase R-U-E, capital F, lowercase A-L-S-E, okay? And this will be a bool, and of course, so these things will not be recognized, and they're reserved words, so you can't call an object true or false or anything like that, okay? Strings can be enclosed in single quotes or double quotes, all right? And these are types str, string, okay? So type hello, hello, and if you need to use in a single quote, that's no problem, okay, you can write you're this way. If you're already using single quotes to encapsulate, then you can escape the quote character using the backslash. Okay. And then we have the none object, okay? This is the none object. It's kind of like the null object, and it's the none. And it has its own type, okay? Type none is none type. Here we can assign none to the name n, okay? And we can ask, is n none, by typing in n is none. And this is gonna return true, okay? There is this thing, n equals none. You can test for noneness by using this, but this is not how you should do it. Okay, this is not recommended. Okay, the way you should test to see if something is none is you use the is question. Okay, there's in memory, there's only one none object, and anything that results in none points to the same exact none object, okay? So there is an object in memory called none, and anything that is none will point to the same ID in memory, and that's how we test for noneness, okay? So make sure if you want to test to see if something is the none object, you use the is operator, okay? N is none, and that's going to return true or false. And here we got if n is none, then print hello, and this will print hello because n is none indeed. Okay, so you can test for that. And so those are the primary types that you'll interact with. There are other types. You have complex numbers, so if you ask for the square root of -1 and things like that, I think. Let me just check. Do I have to do? I'm not even sure. Square root. Yeah, square root's not even defined. I have to from math import square root. Is that right? Okay. So I've got. Where did it go? How did it end up here? Okay. And then let me try square root of -1. Okay, so this gives me an error, but I forget how to deal with complex numbers in Python. So it's just something I don't do very often, but they exist. Okay. All right, we'll first start off with lists, okay? As far as data structures go, there's different data structures, and kind of the first thing that we can work with will be the list, okay? And so you define a list using square brackets, okay? And a list can contain any mix of data types, and so I think this is an example I copied from DataCamp, and it lists off people's names and their heights, okay? So we've got Liz, who's 1.73 meters, Emma, who's 1.68 meters, mom and dad, and it lists off their heights, okay? I guess this is, it's like informal Jane Austen or something, okay. You can, here I've created a second list, and this is a list of lists, right? So here, this first list, fam, has 1, 2, 3, 4, 5, 6, 7, 8 objects in it. And then fam2 is a list of 4 lists. Each of those lists contain 2 objects, okay? Liz in 1.73, Emma in 1.68 is its own list, mom in 1.71 is its own list, okay? And so again, here I'm just assigning these lists and saving them in the objects fam and fam2, and I can ask Python to print these out, okay? And, or actually not even print them out, but I'm in the Jupyter Notebook, I just type the name and it will return that object, okay? And so we have the list, and here we've got the list of lists. When you subset a list, okay, the lists are 0 indexed, okay? Meaning the first item in the list has index 0, okay? And this, again, is just something that takes a little bit of getting used to when you're switching from R or MATLAB to Python, okay? A lot of other languages are 0 indexed, and Python is 0 indexed. So here, fam, you say square bracket 0, and this will return back the first object, or the 0 index object, which is just going to be the string Liz, okay? What will fam2 square bracket 0 return? So looking at this, what's the 0 object, or 0 indexed thing? It's going to be the list Liz 1.73, right? So when I do this, we get Liz 1.73. And so here I can put in square bracket 0, and this will return the string Liz, okay? You can use negative indexing, okay? Negative numbers count from the end and go backwards, okay? So on fam, -1 starts here. So -1 will give me 1.89, okay? So this goes 0, 1, 2, 3, 4, 5, 6, 7, and we can also go -1, -2, -3, 4, and so on and so forth, okay? So here I've got -1, and that gives me 1.89. fam2 -1 will give me this list that says dad 1.89, okay? And similarly, I can string them together and do -1, -1, okay? So the negative indexing returns objects from counting from the end, okay? It's not going to be -0, because -0 is 0, and that's not going to work. Okay. You can slice a list, Okay, this is called list slicing, and this will kind of give you values inside the list. So here, once again, I'm going to just redefine this list here, and I'm going to say fam1:3. Okay, so this will start at 1.73 and end at Emma. Okay, you can think of the list slicing happening at the commas. So 1:3 says basically start at the first comma, start the slice there at the first comma, and go up to the third comma, and this will return 1.73 and Emma. All right, and then here if I do 1:2, what will this return? Okay, it will return the list that contains 1.73. So this is different. Okay, so over here, if I you might ask, how is this different from fam1? What will fam1 return? 1.73, the float. Okay, and this returns the list that contains 1.73. Okay, so it's slicing from the first to the second comma, so the result of the slice is going to be a list. Okay, if I try to slice from 1:1, what will this return? It's going to return an empty list. Okay, because here I'm slicing from the first comma to the first comma, so the result of the slice is a list, but it's empty. There's nothing in there. Okay. Are all of these subtle distinctions okay? All right. 0:2, what do we get back? So a list containing Liz in 1.73. Okay. 6:8. Okay, this will give us the last two, dad and 1.89. Okay, so technically, I mean, there's not a literal comma, there's not a 0 comma here, and there's not an 8 comma there, but you can kind of pretend. Okay, you can do 2:nothing, and this will start at the second comma and go all the way to the end of the list. And here you can do nothing:4, and this will start at the beginning and go up to the fourth comma. Okay. If you do this, what will this give back? There's nothing:nothing. This is going to create a copy of the list. Okay, it's going to copy the entire list. So this is often a quick shortcut to copy an entire list, is you just square bracket with a colon in there, and that's going to create a copy of the list. Okay, this is I'll talk about the difference between a shallow copy and a deep copy in a moment, but for now it creates what we call a shallow copy. If you try to subset with nothing inside, it throws an error. Okay, it says invalid syntax. It says you can't do that. Okay, so fam does this. What do you think fam -5 to -2 will return? The first thing, and then the last thing. Okay, so it starts at the 1.68, which is the -5 comma, 1, 2, 3, 4, 5, down to the -2 comma, which is 1.71. So, sorry, I don't know why I have print fam in there, but there you go. Okay, so the result of this goes from there to there. Okay. You don't have in Python by default, you do not have what we call fancy indexing. Okay, so in R, if you wanted to, you could subset a vector by saying I want or subset a list by saying I want the first object, the third object, and the seventh object. Okay, so this was allowed. You could take a list and you could say I want the first, third, and seventh objects. Okay, that does not exist in Python, and you can use something called a list comprehension, which we'll talk about later, where you can pull it out this way. Okay, where here if you want the first, the third, the objects at index 1, objects at index 3, and object at index 5, it can be done this way. So you've got a list, and here I've got a list of the indices, and here I'm going to subset each list A using the indices, and I'm going to do it for all the indices in B and throw that into object C. Okay, so this is a bit of a workaround, but by default you don't have kind of this default subsetting behavior. You can't just say A square and then square bracket with multiple indices. Okay, you can give it ranges for the slicing, but that's it. All right, so slicing the lists, we feel okay. All right. Another big thing about lists in Python is that the lists themselves are what we call mutable. Okay, mutable means that the list can be modified. Okay, this is very different from kind of object behaviors in R, whereas whenever you did something to an object, it always created a copy of the object or just produced the result. Okay, and you could store that result somewhere, but the original object always remained unaffected. Okay, in Python, if you call certain functions or methods on a list, the list itself will be modified. Okay, so here I'm creating an object called fam. This is the list of kind of our 4 family members and their 4 heights. Okay, and here I'm going to basically store fam in a list called second. Okay, but one thing to remember is that when you do something like this in Python, second refers to the object fam, and it's not a copy of fam. So here I'm going to change the name of Liz. Okay, change the 0 index object from Liz to sister, the string sister. And when I print this out, okay, second will have sister, and then everybody else will remain unchanged. But then when I print fam, the original object, what we will also see is that it too has the first object changed to sister. Okay, so a little bit. So when I run this, you're going to see 3 lines. The first will be fam printed out. Okay, this second thing that's printed out is the result of changing the 0 index object in second to sister. And then this third line is I ask print fam, and when I print fam, we see that fam itself has also been changed. Okay, yes, question?
Is that a type of renaming or evaluation?
It's not a renaming. It's when you call in this command here, second equals fam, is you're creating another object, but you're just setting it equal to this original object fam. You're just creating another name that references the original object.
So there's no benefit.
Yeah, this is not a good thing to do, generally speaking. Okay. Here, this has almost the exact same code. The only difference here is that instead of saying second equals fam, I'm doing second equals fam, and then I've got bracket, colon, bracket. And this bit here, bracket, colon, bracket, creates a copy. Okay? So here it says, so here I've got fam, and then here I say subset fam, but give me back everything inside the list. Okay? And so when I do that, it creates a copy and stores it into second. And then I do the same thing. I modify the 0 index object in second to sister, and then I ask, well, what does second look like? And indeed, we see The second has changed, okay? The zero index object has changed to sister, whereas the original fam object remains unchanged, okay? So don't do this, do this, okay? Where you use fam bracket colon bracket to create a copy. Otherwise, you'll be modifying the original object. Okay, and similarly here I've got fam, I'm doing fam.copy. This is pretty much the same as this. So here, when I do third equals fam.copy, it's going to create this, create a copy of the list fam, okay? So here I say, okay, well, show me what third looks like. This is a copy of the original fam list. I'm changing the index object at index 1 to 1.65, and then I print that out, and we can see the original fam remains unchanged as well. Okay. Here I'm gonna just print out fam again, which looks like this. And if you can use list slicing in conjunction with assignment to change values. So here I want to change the values from the first comma to the third comma to 1.8, and this will be Jenny, okay? And so what I'm going to see is this will change. The result will be what? Liz, this will now read 1.8, and this will read Jenny, and then everything else will be the same. 1.68, mom, 1.71, so on and so forth, okay? And that's indeed what we see. So, you know, you can change the multiple values inside a list using the slicing. But they all have to kind of be adjacent to each other for the list slicing to work. Okay, let's take a look at some of these list methods. Okay, so we already saw list copy, okay? And that's equivalent to doing, if you've got the list A, you can just do A bracket colon bracket, and that makes a copy, and we've already seen that being used. Okay. Here we've got, there's a method called append, okay? So you take the name of the list, and you do the list name dot append, and it will insert the it will append this last thing to the end of the list, right? So here it says add an item to the end of the list, equivalent to saying A. So here it's equivalent to doing A, bracket like 8 colon, okay? So you'd say, 1, 2, 3, 4, 5, 6, the 8th comma there, which technically doesn't exist, and it's appending that there, okay? So here, we can do fam.append, okay? And that modifies the object itself, okay? So, if you recall in R, whenever you run a function, it just returned the result, and it didn't actually modify the original object itself. But here, the object fam is being modified by this method directly, okay? And so here, when I say, after I print the result, okay, fam itself looks like this, where me has been appended, okay? And when you use append, you can only append one object at a time, okay? Or you can't try to append multiple things there, right? You can, if you want to grow the list by more than kind of one item at a time, you can use the plus operator here, okay? So here you can do fam plus the list 1.8, right? But notice that here, I have to save this back into fam, okay? So this is not, the addition operator is not going to modify the original list itself, okay? So here it just appends it here, and here I have to save that into fam. And I get this. Is that all right? So let me just kind of show you. So once again, this is what fam looks like. If I do fam.append, and let's say I want want to do this, okay. And then I ask, what is fam? So here I've asked to append this into fam. What will fam look like now? How many items will be in fam? So fam right now has, I think, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's got 10. So how many items will fam have? No takers? It's going to end up having 11, okay? It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this thing that I've appended gets inserted as one object, okay? So fam has 11 there, okay? This is probably not what we wanted to do. If we wanted to do what I think we wanted, okay? No, that doesn't work. Sorry. All right, let me just copy this thing up here. I can do fam plus this thing. Okay, and so that will now append the 4 objects. Okay, but the key difference here is that if I ask for what is fam originally, has fam been modified? It has not. Okay, because I didn't store the results of this operation. Okay, so append will modify the original object itself, but the addition operator does not. The addition will append it to the end, okay, probably in the way that we were thinking of, but it doesn't modify it directly. Okay, you similarly have an operation similar to append, but called insert, and it's and it inserts the object into the x. Inserts the object at this index I. Okay, so here I can say here's Liz 1.73 and so on and so forth, and we're going to insert at index 4. So where's that? Where's index 4? Is that after Emma and before 1.68, or is that going to be after 1.68 and before mom? Okay, so remember Python, or is it going to be after mom and before 1.7? Okay, remember Python is 0 indexed. Okay, so it comes after 1.68 and before mom. Okay, so you can kind of think of it as where the commas are once again. Okay, so 4, you just say it's going to go into the 4th comma. Okay, and it goes right there. All right, we're going to see the same kind of problem here that we did when we tried to do append with a list, and it's going to insert this list itself into this 4th comma location. Okay, which is probably not what we wanted. Okay. If you try to do multiple things here, it causes an error. Okay. Okay. You can do extend. Extend allows you to take a list. Okay, so here you can do list.extend, and it says iterable, meaning that you can give it like another list here. Okay, fam.extend, and that will tack on this stuff at the end. Okay, and so Joe in 2.0 shows up at the end. Okay, but if I wanted to do this thing where I'm trying to do this, where I'm inserting Joe in 2.0 into this position at the 4th, kind of at the 4th index, but I don't want it to be its own list, what do I have to do? Okay, here I'm going to use a combination of slicing and assignment And here's the thing. I'm going to assign Joe and 2.0 into the slice 4:4. Into this, basically at the fourth comma, we're going to assign the values Joe and 2.0. And so when I do that, that gets inserted there at Joe 2.0, all right? Is that working? Okay, let's take a look at what it means to have a copy versus a deep copy, okay? So by default, copying an object creates what we call a shallow copy, right? And this only makes a difference if you've got objects, like if your object, your list, contains names of other objects, okay? And if it does that, then there's a difference between just creating a shallow copy, which copies the references, versus creating a deep copy, which creates the copies of themselves. To use deep copy, you have to import copy and then use copy.deepCopy, okay? So, for example, it would be kind of like, I don't know, like I've got a list of books, okay? If I have a list of books, you can create a copy of that list, and your copy of the list will refer to the same books that I'm looking at, okay? Now, if you create a deep copy of my list of books, you will create a copy of my list plus entire copies of the books themselves, okay? So you will acquire your own set of books. So if I've got a list and it says I've got The Cat in the Hat and Green Eggs and Ham and I don't know, some other Dr. Seuss book, okay? That's my list, and you can create a copy of it and you can modify that thing, okay? But if you reference one of the objects inside that list, such as the Cat in the Hat book, you will be referencing my Cat in the Hat book, okay? But if you create a deep copy, then you will be basically creating your own copy of Cat in the Hat, and you can modify that. So here, let me just kind of illustrate. Here I've got list A, which is A12, and I've got list B, which is B34, okay? C is going to be a list containing the object A and the object B. And here if I do D equals C, then D references C and D is not being a copy, so they both refer to the same object, okay? So it looks like this. We've got lists of lists. They both look like the same thing. And if I modify the first object in C, or not the first, the index 1 object in C to X, that's this thing, it's going to affect both lists, right? So the index 1 object gets changed to X, and we get this. All right. Here, I can do copy, and this creates a shallow copy. So here I've got A, B, and then C again is a copy of this. D is going to be a copy of C, and here I can modify the index 1 object to X and C, and because D is a copy, when I do this operation to C, it does not affect D, okay? But notice what happens here. Here, I'm going to append the value 100 to list A, okay? And so when I append the value A to 100 to list A, okay, list A will now contain A1 to 100, okay? And because both C and D reference list A, they both get modified, okay? C, we've changed the index 1 object in C to X, and D did not change that. So this still references object B, or list B, B34, but because both of these lists, A and C and D reference list A, when we modified list A, they both got changed. Okay. All right. Here's the example of a deep copy. With a deep copy, I've got A, B, and C again, and E is going to be a deep copy of list C. Okay. And so here, again, because E is a copy of C, when I change index 1 to X in list C, it's going to modify C but not E. So we get this. And now, when I append the value 100 to list A, only list C references this list A. Okay, list E created its own copy of list A, so it's got some other value in here. So appending the value 100 modifies only list A, which is referenced in list C, but it doesn't modify this list over here, which is a copy, which is a copy of the original list A, and that's not modified, right? If we understand the difference between what happened here and what happened here, between the shallow copy and appending something to list A and appending something to list A in this thing, then I think we understand the difference between copies and deep copies. Okay, let's see. We might run out of some time here. If you want to delete something or remove something, you can use remove, okay? And, okay, well, we're about to run out of time. But, so here's the list, and you can do remove, and again, these methods modify the object themselves, okay? And so when we call back for them, they get modified. Okay, we'll end here for now. We'll see you guys on Wednesday. Talk more about these data structures in Python.